Now let's talk about uniform circular motion. First off, what we mean when we're discussing uniform circular motion, what we mean by uniform is that it's traveling at a constant speed. So uniform means we have a constant speed. Not necessarily constant velocity, but a constant speed here. And then obviously circular motion, things going around in a circle. Everything we've talked about so far has been linear motion, things moving in one dimension, or maybe two dimensions was just one dimension one way, then applying the same equations the other direction as well. But now we're going to talk about things moving around in circles at a constant speed, uniform circular motion. So before we discuss this, let's review a little bit about acceleration and velocity. We know that an acceleration is a change in velocity with respect to time, but let's say we have a velocity vector here. So here's our velocity vector, and then let's say we have an acceleration vector which is parallel to this. Then the result of this acceleration would just make this object speed up, right? If we had a particle here with a velocity off to the right and an acceleration off to the right, then the object would simply speed up. It wouldn't change directions or anything, it would just speed up. Conversely, if we had an object which was traveling off to the right, say here we have a velocity vector which is off to the right like that, and then we have an acceleration which is off to the left, or an acceleration which is anti-parallel, then we would have the speed would be reducing, right? So the object would be slowing down, but it wouldn't be turning either, right? So if it's parallel, it'd be speeding up. If it's anti-parallel, it's slowing down, but in neither case is it turning. So let's take a look at another instance here. Let's say we have this particle with a velocity off to the right like this, and then an acceleration which is perpendicular to our velocity. And so this acceleration, obviously, if it has an acceleration, then the velocity must be changing, but there is no component which is parallel or anti-parallel to it. So it's accelerating, and it's not speeding up, and it's not slowing down, so it must be turning. So if we have an acceleration which is perpendicular to the velocity, then it only causes the particle to change directions as opposed to speeding up or slowing down. So in this case, if the particle was traveling off to its right, then it would be turning, or traveling off to the right, it would be turning to its right. It would be going around like this, right? Assuming it's facing the forward direction. So let's see if we can put a couple of these together. Let's say I have a velocity vector like this, and then we have an acceleration vector which is maybe like that. We can break this acceleration into components which are parallel and perpendicular to our velocity. So there would be some part of my acceleration like this. I would call this a parallel, and then I have some portion perpendicular. This would be a perpendicular. And so then we would see that this acceleration is causing this particle to speed up because of the parallel component. It's speeding up here, and it's also turning to its right because of this perpendicular component. So we can kind of look to see what this acceleration is going to do by looking at the parallel and perpendicular components. Just doing another one here. Let's say we have a velocity which is like this, and then an acceleration. So this was our velocity here. And say we have an acceleration which is like that maybe. Then this one would be slowing down and turning to its left, because we would have some portion of acceleration that way, some portion of acceleration this way. Just adding these vectors graphically, we can see that the two red vectors make the green vector. And so then this would be turning to its left, and it'd be slowing down. So if we have a acceleration parallel, it speeds it up. Anti-parallel slows it down, and perpendicular, it changes its direction. It causes it to turn. So let's next look at a object going around in a circle like this. So let's say its velocity is in this direction, following these arrows here. So it's going around in a counterclockwise. I'll write CCW for counterclockwise rotation here. And the velocity at any point, imagine that this is like a rock tied to the end of a string or something. And so if this string were to break at any point, the rock would fly off in a straight line like this. So this is our instantaneous velocity. It's actually a tangential velocity at any point. So the velocity at any point in the object's path is tangential to this path. So it's always a tangential velocity here. And if the magnitude of the velocity is always the same, if we say the speed is constant, so the magnitude of our tangential velocity is a constant here, then that means that no portion of our acceleration is parallel or anti-parallel. However, when we look at all these velocity vectors here, they're obviously different, right? This one's going straight up, this one's going down to the left, this one's going down to the right. So obviously the velocity vectors are different, but it's not speeding up, not slowing down. So the acceleration must be perpendicular. It's causing it to turn to its left here, right? So here's our acceleration, and then there would be an acceleration like this. This one would have to accelerate this way. All these are the accelerations. And actually, if I drew a few more of these velocities, so here's our velocity, then our velocity here. Let's say we have a velocity there. Then a few more acceleration vectors. This would be the acceleration for this one. Acceleration here. Acceleration, oops, that should be down like that. You see that the acceleration, although they're always pointing different directions, there is one way it's always pointing. And this acceleration will always point towards the center. So this acceleration has a specific name to it. We call it the centripetal acceleration. So, or we put an AC, centripetal. What this means, centripetal is Greek. It means center seeking. So it's an acceleration which is always towards the center. So it's the center seeking acceleration, AC. Although sometimes, if I just redraw this here, our velocity was always tangential, right? So here's velocity tangential, and the tangent is, it goes through one point on the circle, right? But a tangent line is also always perpendicular to a radial line. So if I were to draw a radial line like this, then the velocity, the tangential velocity, is always perpendicular to this. So it follows a line which is perpendicular to a tangent line, which is a radial line. So sometimes the centripetal acceleration is called the radial acceleration. So we have radial acceleration, which we denote as A and then underscore rad. This is the same thing as the centripetal acceleration. So the centripetal acceleration is the same exact thing as the radial acceleration. It just depends if you want to use Greek or English to describe it, I suppose. But they mean exactly the same thing. So oftentimes radial acceleration is easier to say, but centripetal acceleration is easier to write. So I might say radial acceleration but write AC. They mean exactly the same thing. So let's take a look at the magnitude of this centripetal acceleration. So I think, if you have different circles, if you have a smaller circle, it might have to accelerate towards the center faster. Also, if you go faster in the circle, you're going to need a larger acceleration as well. So the magnitude of our centripetal acceleration depends on both the speed the object is going in that circle as well as the radius. And so our magnitude here is v squared over r. And this is, this v is not the velocity, it's the speed squared divided by the radius. And the radius is simply, same thing in a circle, the distance from the center of the circle to the object, which is rotating around. So the magnitude of the centripetal acceleration, which I'll typically just write AC, not writing as a vector here, is equal to v squared over r. And this is just the magnitude. The direction is always towards the center. One last thing to look at, we might be given the speed, but we might not be given the speed. We might be given the radius, or maybe not. But if we have something traveling around in a circle, and we are given the time required for one revolution, which is what we call the period. So the period, which we use a capital T to denote this. This is why we use lowercase t for our time, the kinematic equations. The period is a capital T, and this is the time it takes for the object to go through one full revolution, or one rotation. So the period is the time for one revolution. And obviously the distance, if it goes through one revolution, the distance it goes is going to be from here all the way around, which would be the circumference, right? So the distance would be equal to the circumference. And so if I want to find the speed of this, since we know that speed is the distance divided by the time, the distance it travels in one revolution is the circumference. The time is the period. This is going to be equal to the circumference. Write circumference out here. Divided by the period, since both of these are for one revolution. Circumference is the distance in one revolution, period is the time in one revolution. And so then breaking this down, we can see that our speed is 2 pi r over t. So then our centripetal acceleration, or radial acceleration, this was v squared over r. Then this is 2 pi r over t squared over r. So this is equal to 4 pi squared r squared over t squared all over r. This is all over 1. And so what this reduces down to, our centripetal acceleration, which is the same thing as the radial acceleration, is equal to v squared over r, or 4 pi squared r over t squared. These are all true. So dependent on if we're given the speed and the radius, we can use this one. If we are given the period and the radius, we can use this one. Or you can always find the speed. If you want to go back to here and find the speed and plug it into v squared over r, that's fine too, but this is more straightforward. Most of the work is already done for you there. So when we have an object going in uniform circular motion, constant speed, it has acceleration which is pointed towards the center, and the magnitude of this acceleration is v squared over r, the speed squared divided by the radius. Later on, we'll look at some other accelerations. When we get into chapters 9 and 10, we might look at some other accelerations which are not entirely perpendicular, so maybe like this, in which case it has some perpendicular component and some parallel component, so it can be speeding up and rotating. But in chapter 6, we're just going to limit everything to only perpendicular accelerations, so only this centripetal acceleration for now. We'll add on another layer later chapters.